forces on moving charges on wires, and we also did the boundary conditions. H stand 1 is H stand 2, and B normal 1 is B normal 2 in the region. So, any questions regarding any of that? Yeah. Shoot point?
Sorry, 4.25.
All right, can you tell me what it is?
Finding current density.
Find the current density, go ahead.
It gives you a 3M, 60 degrees, and 4M.
What, say again? Just tell me.
It's find current density at 3M, 60 degrees, and 4M.
3 meters, comma 60 degrees, and what?
4 meters.
All right, so this is going to be, that's cylindrical coordinates, right? That's rho, phi, and z. Go ahead.
For H equals Z over sine phi.
Z
Yeah.
over sine
Phi.
phi.
In A phi, or A rho direction, minus rho squared over cosine phi. In the AZ direction, and that's it.
All right. Well, what they really want is J at this point, right? This is a straightforward turn the crank problem. Here we know curl of H is equal to J. Follow me on this, everyone? We're going to evaluate the curl of H in cylindrical coordinates, then put in the actual coordinate 364 to find out J. This is a very straightforward problem. So if you look at the back of the book for curl of H, I don't have my book with me. What you're going to see is they'll have Cartesian, they'll have cylindrical and spherical. I'll give you these things I'll give you for sure for cylindrical and spherical. For cylindrical, off the top of my head, I don't know how he did this because there's 3 or 4 ways to do this. He doesn't put it with a matrix in his back, does he? He doesn't have a determinant or anything. Can you just tell me the form he has in the back book? It's 1 over rho what?
1 over rho d phi az minus
d phi hz, right?
Or yes.
And go ahead.
And then minus d dz h phi.
Right.
And then
In the a rho direction, right? Pardon me?
You're right. Correct.
Keep going.
And then that's added to d dz h rho minus d d rho hz in the a phi direction.
Right. Plus. Finally.
And then 1 over rho d d rho a phi for h phi minus d d phi
Minus d.
d phi h rho
Yeah.
in the a phi direction.
I'll mention this one time. This is simply applying the derivative defined by that. It's a vector derivative. And evaluating the points. Now, this is not tricky at all, but if you look at this right here, this is H rho, and this is HZ. I'm making this point because there are times people don't understand. They're just the coefficients of the unit vectors. Y'all follow me on this class? They're functions, but they're coefficients at the same time. So if we look here, there is no A phi. Y'all follow me? There's no H phi. Since there's no H phi, the smart thing to do is get rid of anything with H phi right off the bat. This is the way I do it. Now, if you look at the next thing, for HZ, this is HZ. Y'all follow me? I'm going to take the first derivative. This part right here, now we're going to go here. Let me see, is there H rho? Phi there is. Okay, that looks like those are the ones we have to evaluate. If you look here, I have curl of H equal to J equal to 1 over rho. Now I have the derivative with respect to rho of hz, which is this, right? I'll even put it in here to do it one time. So I have rho squared over cosine of phi, right there, and that's a rho. Plus, then I have the derivative with respect to z of h rho, which is this. Minus the derivative with respect to rho. That's derivative with respect to z of hz, which is rho squared. It's actually minus rho squared over cosine phi. And this should be a minus right there.
Dr. Baginski?
Yeah.
On the a rho direction, you're actually taking the derivative with respect to b, not rho.
Yeah, that sounds right. So this is with respect to phi?
Yes, sir.
Yeah, that would be right. It has to, because you're never gonna take a derivative, you'll never take a derivative of, with respect to like rho of h rho if you're doing a curl. It'll always be, this quantity and this quantity will be orthogonal, always, when you're doing a curl evaluation. So it's a phi I just wrote them down, then I'm gonna talk through this fairly quickly. Do y'all follow me what I've done here? I've replaced the either hz or h rho terms with the quantities that are over here. Y'all with me? Now, if you look at this, most of the time you can just go through this in a heartbeat by taking one look. Y'all see that this is with respect to phi, and I've got rho squared with a minus sign, and I have 1 over rho. So it simply brings out minus rho there. Do y'all follow me on that? Now if you take a derivative of 1 over the cosine, somebody was in my office the other day, they were talking about this. What we really got here is the derivative with respect to phi of a functional form, which is cosine phi, right? And this is to the -1 power. Now I wrote it this way because a lot of times when you're doing these things, you won't remember how to take the derivative of like 1 over cosine squared or 1 over secant squared, but you'll know what the derivative is of a cosine or sine or tan. That you know. So write the functional form. This is 1 over cosine, right? And that would be what? Secant, correct, class? 1 over cosine? Some of you may know this. Well, this derivative you know, don't you? That's going to be -1 over cosine squared of phi, and then the derivative of cosine is sine, right? Sine phi. Do you agree with this, class? It's actually what? Minus sine, isn't it? Right? Cosine goes like this, sine goes like this, right? Derivative would be minus. So it'd be minus sine. So this first term right here can be replaced by simply sine phi over cosine squared. Did you ask me about this problem? I thought that was the one. And you could write this like sine over cosine is tan. So this could be tan phi over cosine phi as well. They're both the same. You follow me? Different forms, same exact values. All right, so that's that part, that's a rho. Now when you look at this one, it's ddz of this. Well, ddz of just z is 1, right? And sine phi is of no function there. I mean, sine phi doesn't vary. So it's just 1 over sine phi. And then for this one, I got derivative with respect to rho of minus rho squared. I know derivative of rho squared is 2 rho, right? Follow me? And when I do this, I got a minus there. I can replace this by And finally here, it's the derivative with respect to phi of z over sine phi. Y'all follow me? So if you're gonna do that one, again, the minus z just comes out in front. Then I take the derivative of sine phi to the minus 1, which is a minus, makes it plus. Then it would be of 1 over sine squared. And then the derivative of sine is cosine phi. And that's it. Y'all follow me? You're just doing the derivatives. That's the only thing you're doing. Now once we have that, we have to evaluate it at the position that they gave. So the position was 3 meters, rho is 3 meters. And you can do this any way you want, but let me just see about this. 60 degrees and 4 meters. Is there anything that's gonna fall out easily? Unfortunately, this is one we're gonna have to probably brute force. So rho 3 meters goes here. That's 3. And then for phi 60 degrees, let's see. Sine of 60 is square root of 3 over 2. Cosine of 60 is 1/2, right? So I got that's 1/2 squared. So that means I really have 1/2 here squared. You can evaluate that. Well, you can see what's going to happen here. I'm going to end up having a 2 come on top. And your calculators will do this for you in a heartbeat. So this is going to be times 2 here. Sine of 60 is square root of 3 over 2. And cosine of 60 is 1/2. So that means it's 4 times 3 here. And then finally, and you can simplify it as much as you want. The last one's going to have a 2 squared come up top times 1/2. So it's just going to be 2 over 3 here. But that's all that one involves. Anytime you're taking a curl, or finding J from a known H field, you're taking the curl of H and evaluating it at the point. There's really no trick here, but it just takes a little time. Is that the book's answer, by the way? You asked me that.
The book's answer is -10, A row plus 13 AP.
-10. I'm not sure exactly how that works out. That's not -10. What's close?
It ends up being like 10 point
That's that.
something.
That would be that. Because that's what, 6 times square root of 3, right?
Comes out to be 10.4.
That's right.
Yeah,
But that's how they do it. Huh?
I got positive 10.4.
And that would be probably the book's answer. But you all see how I did this? It's a minus sign there, right? In front of it. That's all. Those are not that big of a deal. Any other questions regarding Bobby?
4.50.
Okay, hang on. Go ahead.
The plane y equals 0 separates two magnetic media. Medium 1 is
Let me put this Y. Okay.
medium 1 is the negative y, and it has a mu relative of 3. medium two has a mu relative and the sheet current of 1 over mu naught.
This is 1 over mu naught, what direction?
AX.
So if we had X coming out of the board, the sheet current's this way, and it's K is equal to 1 over mu naught AX, and that's amps per meter? Amps per meter? All right, for this problem, there's 2 laws that we're gonna, the first law is just B normal 1 is B normal 2. Do y'all remember that, class? So let's go ahead, and they have to give us an H field somewhere.
It gives you B1
All right.
is equal to 4.0 AY plus 6.0 AC. Webers per meter squared.
AZ, yeah, Webers per meter squared. All right, if you take a look at that, thing is, break it down to a normal and tangent component. You all see the normal component, the boundary here is coming out of the board, it's planar, right? The normal component's piercing this region in this direction. Y'all follow me? That region would be 4AY, right? Y'all with me? So this would be the normal component. And I know automatically B normal in region 2 is B normal in region 1, and that means it's equal to 4AY. Takes care of that right off the bat, correct, class? Next, we have to find the tangent value. Well, obviously, this is the tangent value, right? It's AZ. AZ would be in this direction. Correct, class? And it's flowing at the interface of these 2 boundaries, right? So now you can do this a couple of different ways. And I had, I wanted to put this down. I don't know if I put this exact expression down last time, but this is the one he has in his book. There's a couple of different ways to write this, but if you have medium 1 and medium 2, and I'm taking this from his book, then I can say, if I have A21, which is a unit vector that points from region 2 to region 1, I can go and I have a surface current K here at the interface of these 2 things. I can say A21 crossed into, and it'll be H1 minus H2 is equal to K. Now I wrote the whole thing down there, but I'm going to explain why I did so. That's the formal law, but I told you already how to get that. Well, last time I went through it with you, but maybe this isn't so obvious if it's applied over here. So, I have the boundary planar, this is vertical, the boundary. So if you think about this, this is region 1, this is region 2. So here, my A21 would point in that direction. Do y'all follow me on that? Now, how many, did you see this in the book? I don't know which figure number it is, but if you can tell me, it may help somebody. This is a good problem because it makes you more of a bookkeeper, but you're going to see the simple physics at the end. Anybody? While you're getting that, A21 for this one would be what? Minus AY, as drawn. Do you agree with that? Now, after we have that, we have H1 and H2. Here, I'm going to go ahead and just use this law. I have A21, which is minus AY, crossed into, and then it's H1 minus H2. Well, in order to get H, I have to take my B field, right? And I know B is equal to mu H in region 1. And if I want to get the H field, I have to take B1 divided by mu to get H in region 1. So I come over here, and now I have 4AY plus 6AZ over mu naught, and then mu relative in region 1 is 3, and that's really H in region 1. And then to get H in region 2, that's what we really want. We know that that's 9. And then B in region 2, I know I'm gonna have 4AY, but I'm also gonna have some unknown value for B2 in the Z direction. I'll just call B2AZ. Call BZ2 right there. The reason I've done it this way is I'm gonna show you just by throwing it into the formula, that AY stuff crosses out to 0. You're gonna see this in a second, all right? So I'll put in my H1 is this. You're gonna see this in a second. So I have 1 over mu 0, or 1 over 3 mu 0, times the quantity 4AY plus 6AZ minus, and then it's H2, and that's 1 over 9 mu 0. We already know the AY component, but we don't know B in region 2, the Z component of it, and it's AZ. And all this is equal to K, and that surface current was 1 over mu naught AX. Now you don't need to do this if you got no surface current. Hear me on this one. If you have no K, then H tan 1 is H tan 2, B normal 1 is B normal 2. Please remember that. H tan 1 is H tan 2, B normal 1 is B normal 2, right? Because 99.9% of the things you're gonna run up against have that basic condition. Do y'all follow me? All right.
Can you say it one more time? just the equals each other.
This, if this is 0, the normal components of the B field are the same, B, like I did there. And the tangent components of the H field are the same. It's very similar to electrostatics, where if you have no surface charge, then you have E tan 1 is E tan 2, and D normal 1 is D normal 2. Same basic type of problem. I mean, it parallels the effects, all right? And that's standard for 99.9% everything. All right, so if I do this and you take one look at this, and I wrote the whole thing out for you, get rid of mu naught. You all see how mu naught appears everywhere on both sides? Just multiply by mu naught so you don't have to worry about it. Now after that, here's the next thing I want you to take away from this. You see I have AY crossed AY, right? Right here, don't I? What is AY crossed AY? 0. And I got it there too. In fact, you'll see the normal components are things you don't even worry about here. Only the tangent components when you go A21 crossed into the H field. Can you all see that? So I just get rid of this component and this component. Y'all with me? Now this is 1. Now finally, I'm gonna do this. I have AY crossed AZ. AY crossed AZ over there, correct? What's AY crossed AZ?
AX.
Y cross Z would be AX, positive AX, right? I got AY crossed AZ, that's positive AX. I'm gonna leave the minus sign here. So it's positive AX. And this is gonna be 1. Did I have a minus sign twice on this one? I think I did. So that's B2AX here. Now, in a nutshell, what happens is this. I have, and there's a minus sign, so I have B2X over 9 minus 6 over 3 AX, all of them, is equal to 1. That's how it's coming down in my math. Y'all follow me on this, class? You don't? Oh, you do, okay. I wanna make sure. If you don't, let me know. And the only thing here is you take one look at it, and what do you see? This is 2, right? That means this has to be 3, doesn't it, class? So if this is 3, that means what? That's 27, isn't it, class? 27 where 9 would be 3. So it looks like B2X is 27. And you'd find the total B field in region 2 as 4 AY plus 27 AX, and it would be Webers per meter squared. I don't know what the answer is, but that's the way you go about it. The real problem with this is you're not familiar with this kind of crossing right here. And what I normally tell people to do, well, I showed you the way I do it last time, but when you have a surface current vector right here, first do the problem without the surface current vector. H tan 1 is H tan 2. Then if you put the surface current in there like this, what it simply does is cause the H field on the side above this to go up by the surface current's value. And the surface current, let me just explain this. See how the surface current has a value of 1 over mu naught, right? But if you got rid of the mu naught, it's just 1. You all follow me on that? Now, before that, the value of, it's really the B field over mu relative was 6 over 3. So the B field that was already there was 6 over 3 when you normalize it with respect to mu relative, which is 2. Add 1 to it, you get 3. That's what this is. I'm not saying this the way I'd like to, but I'm going to tell you, once you do some of these problems, you'll see that you're really just getting rid of the effects of B and adding the surface current value to the value of the B field on the second side. That's not gonna sit well with you. Use that equation if you're worried about it, and I'll give that to you if you need it. But I'm not a real fan of the way they do it there. But the way I'm thinking about explaining it, I don't think it's gonna make a lot of sense to you until you get a few other things under your belt in electromagnetics. Okay. Other questions before I continue? I got a couple things I want to do today. All right. Now, we've covered basic forces. Next thing we do is cover torque. And then after torque, we're going to cover inductance. That's the goal. So, next thing is torque. My neck shoulder area is still bothering me, but it's a lot better. Here's why we cover torque. Because everybody who's an electrical engineer should at least have a basic idea of rotating machinery. You have Gross already, right, for your power course. Did he do rotating machinery? If he's done it, this is old hat to you, but I have to cover it just in case somebody didn't get it. So with torque, in general, any torque assumes you have a point, and then you have a lever arm, some distance R away, and then you have a force on that lever arm. And the torque about that point, they call it the anchor point a lot of times in statics and stuff. Torque is always symbolized as the tau is equal to R cross F. Which means is that the torque will always have a vector sense that will be perpendicular to both the R vector from the anchor point to the point where the force is applied. Now, did you have statics already, class? You have basic stat? How many have? You probably got this from Gross, but I don't know. So the torque would always be perpendicular to both. And the further the lever arm is, the more torque about that point for a given force. And torque will always be in Newton meters or in what, foot-pounds in statics if you have the, somebody that teaches out the English units. But generally speaking, it's length times really the force in whatever units you want. That's torque. So in electromagnetic torque, it's the most common way they start is, and in Wentworth's book he does this, he says if I have this is X, this is Y, and this is Z, and now I have a loop here that's going to conduct current, and I'm going to have the current conducting this way. That's the direction of current, flowing this way. So it's flowing in the clockwise direction looking down the Z-axis. And I call this dimension A, and it doesn't really matter, this dimension B. And then I gotta put a B field. So now I put a B field in this direction. So it's in the Y-axis, but I'm just gonna leave it in the most general sense. I'm showing you the B field going that way. Now work with me on this one, make sure you see it. So if I have IDL, remember the differential force is equal to IDL crossed into the B field, right? So follow me on this. If I have IDL on this is in the AX direction, this member here, which way is the force? IDL, right? I've got the B field going the Y direction everywhere, it's the same, right? So I got IDL, think of it coming out, right? Crossed into B is up, yeah, AZ, y'all see it? So that would be the force on this member, right here, and it should make sense. Now what about the force on this member? Take a good look at this before you just turn yourself into a pretzel. I got IDL this way, what direction?
Negative A1.
Crossed into B, what direction?
Positive A1.
Is
0.
no force. Y'all hear me on that? Whoever said that's right. There's no force there. As a matter of fact, there's no force on this member. Anytime the current is in the same direction as the B field, there is no force. That's one thing you make sure you get. No force there and there. What about on the last one here? Well, here the current's going in this direction, right? Which way is the force? IDL crossed into B, down. Y'all see that? As a matter of fact, this force here will be the same as this force here in magnitude because it's a rectangular loop. Y'all follow me? B field doesn't change, current doesn't change. And what that does is tell you there is no net motion to the loop. There is no translational motion because the net force is 0 on the loop. Do y'all follow me? But there is a torque, and the way torque is always established on a loop is down some axis of symmetry. Y'all see how right down the middle there, at about B/2 from this axis, what that torque will do is rotate the loop this way. Do y'all see that, class? Can you imagine, right? So let's just see what goes on here. If I've got that coordinate system, X, Y, and Z, the B field's going out there, so I'll just say that's equal to some B0 AY. Then I can say the force right there, I'll just say this member, call it 1, would be equal to I times L. We really don't need a differential here, so it's going to be I, whatever it is, times L. And L here has a magnitude length of A. That's what this side's length is. It would be in the AX direction. Wait a second. Yeah. And it's that crossed into the B field, which is B0AY. And that gives me a force of IA B0, and it would be in the AZ direction. And that's true, that's the force. That's in the, and then F2, this force, call this F1. F2 would be equal to minus I times A B0 AZ. I'm only putting these down for completeness. Y'all follow me on that? That just gives you the relative magnitude based on the assumptions. Now the torque you have to have that axis that it's anchored at. You see how this thing's gonna rotate about this position? Can y'all follow me on that, class? It assumes a few things. Basically that the loop is equally weighted, that it's floating, you might say, there's no gravitational force. But that's the way it's gonna move, and it's anchored there if it was allowed to move. So this lever arm is actually B over 2, and this lever arm distance is B over 2. Now the reason I say it is when I get the torque about this point, remember, torque really is R crossed into F, right? Now we have two R's. We're gonna have an R from here to here and an R from here to here. But I wanna show you something before I just start writing equations and bothering you. Just stop and think for a minute here. The way you always think of torque is with your right hand. If you have an R and an F, if I'm coming down this axis and I know it's gonna turn about that axis, use my index finger on my right hand, point in the direction of R, and then cross that into the force, F. Your thumb points in the direction of the torque vector. Can you all see that, class? Now, which way is it gonna point? It's gonna point in the AX direction, right? So, I mean, mathematically, you're gonna see it in a second, but there are two torque vectors. Remember, this length is B over 2. So it would be actually B over 2. And that would be AY crossed into the force, which is going to be B0 AZ. Now, that would be the torque caused by this member, and the torque caused by this member will be identical too. The thing is, here, the B would be minus B0, then it would be plus minus B over 2 AY, and it would be crossed into, and then this would be minus IA B0 AZ. And here's what really happens if you look at this. I'm trying to do this in a way that I'm cutting to the chase on this one. This torque is equal to this torque in magnitude. You can see those two minuses basically cancel right there. And the net torque on this is simply going to be BAI times B0, and it would be AY crossed AZ is AX, and that would be Newton meters of torque. Now I'm doing this in a way that probably is very simplified, but I'm going to show you a trick that saves lives. It'll make it easier on you. Now, you know, in engineering, we always try to find the easiest way to fashion and formulate a problem to get the solution. We don't need things to be as complicated as possible. They get that way on their own. We try to reduce the complexity. So here's a trick. You see, that only works for a rectangular loop with one turn, right? If you had two turns, you had shellacked wire on top of each other, the torque would double. That should make sense. If you have n turns of wire wrapped around with a current, you would have n times that much torque. That makes sense to engineers. But what happens if you had a circular loop that was in the plane? Or what happens if you have an elliptical loop? This is the easy way to deal with that. Now there's one condition though. Write this down. This is X, Y, and Z. You have to know that the loop you're talking about is in the XY plane or in the plane that is perpendicular to the B field. So I'm putting the B field in this direction now. I'm going to have the B field in the Z direction, right? Y'all with me? Now this loop has an area. If it had a radius A, it would have an area A equal to pi A squared. I hope that makes sense to everybody. With me? We got a loop. Doesn't matter if it's a rectangle, if it's a square, if it's a hexagonal, or if it is something that's a circle or an ellipse, as long as it lies in the XY plane or in a plane that's perpendicular to the B field. This is the key. Then what we do is we find something called a magnetic, and it's really a magnetic dipole moment. I don't know if Gross showed you this or not. The symbol is M, and it's a vector. Now here, M is equal to the area of the loop. In our case, it would be pi A squared. Here, area would just be pi A squared for this loop. But whatever the area is, if it's hexagonal, it's different. If it's rectangular, it's different. But that's just the area. It's a scalar. You with me? Meter squared. Area, and it's got to have a unit vector that is in the direction your right hand would give you if you knew the current direction. Now let me show you what I'm talking about. So if I have a current going in this direction, I, y'all with me? Take your right hand and grab the current. In the direction your fingers are rolling around, I mean, you gotta have it go in that direction. Your thumb points in the direction of M. You see how it's going straight up? It's in the Z direction. All right? It would be AZ here. So I'm just gonna, and it's times I, by the way. So this would be area pi A squared. Then it would be times I, because that's the magnitude of the current I'm assuming flowing. That would be it, and it would be in the AZ direction. Now question, and it's a no-brainer. What happens if the current's going in the opposite direction? The only thing happens is it becomes negative. You all see that? This is called a magnetic dipole moment. This is nice to know, and I'll tell you why. Because now the torque on that loop, right there, is just equal to M cross B. And this is in his book, I think, but I don't have that. Now, that means, see, getting the magnetic moment of a single loop is easy. You all agree with that? Just think of the last problem. We know the current, we know the area, we know the vector sense of I, right? I mean, we'd have to use our fingers. It's much easier to use this formula to get torque. Now that's for one term. What happens if I have more than one? Just multiply by n. Now how many know that rotating machinery usually have a rotor, or whatever you want to call it, that has a whole bunch of turns, right? The most basic DC machine, the maximum torque you get is the approximate B field that's penetrating that perpendicular times the number of turns. It's going to be the magnetic moment of one of those turns. So it's the area times I, times the number of turns, times n, and then times the magnetic field would be the maximum torque you get. But that tells you so much about a DC motor. Did Dr. Gross go through the difference between DC and AC motors? How many have had Gross? Did you have him in power, did he do rotating machinery or not?
We did Stater,
Yeah.
right?
Pardon?
Stater fields and.
Yeah, so he did talk about AC versus DC motors. Okay. It's important at least you have an appreciation, and here's the real reason. A lot of you guys are going to be working in the industry of electric vehicles or things where you're talking about going from gas to electricity as a power source, and they're going to be talking a great deal about something called energy scavenging. You know the brakes on a lot of cars, like my wife's, she has a Camry and it's a hybrid. The brakes themselves recharge the battery, it's energy scavenging. But she also has an electric motor in the vehicle that runs most of the time. The motor itself, the whole thing is that motors can be generators, generators can be motors. And it's very interesting to see how a basic understanding of mechanical and electrical engineering with this stuff will allow you to understand almost the entire EV, the electric vehicle industry and the hybrid industry. And they're looking for people like you in both camps. Have you all had statics here or not? You've had statics, have you had dynamics? And
Engineering
Some have, some haven't. Those courses are gonna be key to a lot of things you do later in life, probably. All right, I didn't get to my goal, which was inductance, but I will on Monday. I'll give you a test or a quiz, but would you do me a favor? Spread out and I'll move people as